These shells are composed of curved beams that deform elastically under external forces. The rods are laid out in flat assembly state and connected with single-axis joints. Upon actuation, beams must bend due to the geometric incompatibilities introduced in the flat layout. The beams can be optimized so that the deployed state better approximates the prescribed target surface while minimizing its elastic energy. If you want to know more about how we leverage numerical optimization and geometric abstractions to design our structures, please attend our talk. Thank you.
So volumetric simulation is well known, and there are many volumetric materials used in the literature. However, the same is not true for thin shells, and we fix this problem in our work. We demonstrate how to simulate thin shells under arbitrary hyperelastic materials such as Arab, co-rotational material, neo-Hookean, and so on. And this is done by expanding the volumetric elastic energy in a Taylor series as a function of the thickness of the shell. And here are some of our results.
Based on a concise matrix expression of the dihedral angle Hessian, we introduce a novel analytical eigensystem and adapted geometric stiffness to enhance the stability of dihedral angle-based bending models. Our approach facilitates stable simulations of fabrics with a diverse range of physical properties, spanning from fabrics with low bending but high membrane stiffness to those with high bending but low membrane stiffness.
Thank you.
We propose a novel subspace preconditioned projective dynamics framework for efficient high-resolution cloth simulation. The key idea is to combine subspace integration and parallelizable iterative relaxation. Low-frequency motion modes are resolved within the subspace with a prefactorized subspace global matrix. The high-frequency details are dealt with using parallel Jacobi relaxation. A time-splitting scheme along with a quadratic contact proxy is used to handle complex contacts efficiently. Our algorithm runs efficiently on a single GPU. The comparative evaluation demonstrates up to 10 times acceleration over the state-of-the-art simulation techniques.
Thin shell structures are everywhere. Fine mesh simulation is accurate but too slow to give interactive user feedback. Coarse simulation is fast but generates unacceptable artifacts. Last year, we presented a progressive solution to bridge this gap. However, it's currently severely limited to a hierarchy generated by loop subdivision. So we present PSQ to extend progressive simulation to support the high-fidelity modeling and design of all input shells and their unstructured triangle meshes, which captures the wrinkling, folding, twisting, and buckling behaviors with frictional contact. Please come to our talk this afternoon.
Introducing case, learning conditional adversarial skill embeddings for physics-based characters. Case enable physical characters to learn various skills with high efficiency and effectiveness. It achieves the top performance in skill embedding. Once trained, case also offers an explicit control handle that allow the user or high policy to control the characters to finish different kind of tasks with desired skills, like those in the video game. Check our session for more details. Thank you.
How many hours does it take to train a physically simulated character? 20 hours, even more, for each new task? No more. We propose AdaptNet, which quickly adapts trained controllers for new tasks. Now it takes less than an hour to learn new controls from existing locomotion policies, change the style of walk, or make characters with different body and joint variations. AdaptNet can also modify for new terrains. Please join our talk. We will show how AdaptNet updates a pre-trained control policy efficiently for these and more tasks.
In this paper, we proposed a new imitation learning framework that can produce diverse and natural human skills And then we can reuse the human skills to solve the new downstream task. As you can see, the 2 players boxing game. If you are interested in our work, welcome to our presentation in the afternoon. Thank you.
We present Muscle BAE, a simulation and control framework for muscle-actuated characters. By leveraging muscle space control strategy based on PD control and variational autoencoders, our character can perform various tasks, such as random sampling and speed control. We incorporate fatigue dynamics into our policy and world model to create a natural evolution of motion style caused by the accumulation of fatigue from prolonged activities. We show the change of the motion style during the development of muscle fatigue with different fatigue rates.
Our attention for more details. Thank you.
Controlling large-scale multi-body animations can seem like magic. With animation control, you can tame pachinko machines to help them preserve rainbows. You can win any game of Yahtzee, no matter how you shake the dice, and no matter how many dice you have. So what's the problem? Well, the problem is that this is slow, often taking hours or days of computational effort. But our algorithm, VICMA, can perform animation control using barely more computational effort than running a single simulation. Now, they say that a magician never reveals their tricks, but just this once we'll make an exception at our talk.
Hello. Have you ever watched these popular water bottle flipping videos on the internet, and have you ever tried them? Through trial and error methodology, people even build robots to do it. However, it is more difficult than it looks like. So we are wondering, can we design it computationally? We present DIFFR, a differentiable SPH-based fluid-rigid coupling simulator to help you out. There are also many other interesting tests in our paper, such as stone skipping, water rafting, on-water inverted pendulum, etc. For more information, welcome to our session this afternoon. Thank you.
For high-quality remeshing of TED meshes to hex meshes, a key challenge is aligning virtual grids to boundaries and features. Existing global approaches often yield defects in both grid map and hex mesh. Our approach instead divides the hard global problem into multiple cuboid maps, for which robust solutions are readily available. To this end, we partition the input volume into cuboids and eliminate any unwanted blocks, patches, or arcs using a set of novel collapse operators. These maintain the validity of the partition's embedding at all times. In this way, we can guarantee valid grid alignment and hex meshes free of defects.
When building constrained Delaney tetrahedrizations out of surface meshes, the famous TEDGen software represents the state of the art. Unfortunately, this software fails on 8% of the valid input models due to both numerical instability and a subtle theoretical flaw. We have developed a novel arithmetical framework rooted on modern indirect geometric predicates, and, based on that, we have implemented a variation of TEDGen's underlying algorithm which is both robust and formally correct. Our version succeeds in 100% of the cases while remaining competitive in terms of efficiency and memory consumption.
We propose a method to generate high-order tetrahedral meshes. This means the elements are not straight but curved. Our method is not the first approach, but it's the first to guarantee two important properties at the same time. First, regularity. This means there are no degenerate or inverted elements in the mesh ever. And second, conformance. This means we can prescribe arbitrary polynomial boundary surfaces and the mesh will exactly match this curved boundary without any approximation error. All this is guaranteed by construction. The key is constructing the mesh in multiple layers, finally reducing the problem to classical straight linear TED meshing.
Developable surfaces are often used in architecture for their aesthetic qualities, such as the straight contours, which provide an elegant counterpart to the curved components. Traditionally, they were modeled with paper, but using a physical material limits the design space. We will be presenting our new mathematical model for developable meshes, which allow for unrestricted interactive geometric modeling, even though sometimes the developable design might not be the nicer one.
Provably nice and fair meshes can benefit from double curved faces. We had a closer look at the most simple double curved shapes, namely spheres. Our sphere meshes have circular arcs as edges and spherical caps as faces. As such, they are objects of Möbius geometry. A large class of sphere meshes offers enough degrees of freedom to ask for prescribed intersection angles and offsets. Everything that we can do precisely in those special cases can be done in the least square sense to reach real-world tolerances. Come to our talk to learn more.
We design flexible microstructures that emulate desired materials at finite strength. As strain increases, material properties change in ways that past approaches cannot control. To characterize these properties, we introduce an efficient nonlinear homogenization technique based on adaptive high-order interpolation. We then optimize the microstructure geometry to fit these properties to a target material model. Self-collisions occur frequently at larger strengths, and we propose an efficient scheme for avoiding them. We validate our tools by designing a large catalog of as linear as possible metamaterials, achieving a significantly improved property fit. We verify these improvements by printing and testing samples. Please see our talk to learn more.
Thank you.
Ever had an online shopping experience where you are hunting for the perfect shoe cushion, but it is like trying to find a unicorn wearing sunglasses in a blizzard? Have you ever daydreamed about sprinkling a little of that metamaterial magic into your kick, so that you can stand out comfortably as a fashion supernova? Well, hold on to your socks because we just got the shoe for you. Please come to our talk on neural metamaterial networks for nonlinear material design.
Are you having trouble finding a sparse network of cables and struts that balances a set of input forces while avoiding obstacles? Well, don't stress. We can find one using insights from geometric measure theory, compressive sensing, and continuous optimization. And it can be used as an initial step in building more complicated structures. Please come to our talk later today to find out more.
So you want to 3D print a surface, but you don't want to do it the boring old way? How about smashing it into a flat surface, printing it like that, and just by heating it, it morphs back into the surface you wanted? Introducing shrink and morph. We exploit the shape memory effect of PLA, which shrinks when heated, and optimize the printing trajectories to control the morphing of flat shells. And the best part is that anyone can do it with a cheap 3D printer. Come see our talk this afternoon for more shrinking and morphing.
Additive manufacturing excels in creating complex models, while subtractive manufacturing enhances surface quality, and hybrid manufacturing combines their strengths. Deploying the AM then SM sequence only once might result in persistent collisions in some regions, while too many sequences will result in expensive switching costs. For achieving our objective, we transform it into a volume and surface co-decomposition problem, named VASCO. Here shows the optimal decomposition result. The model is decomposed into 3 AM then SM sequences by our VASCO method.
Thank you.
Ever consider the unexpected behavior of a spinning golf ball at different Reynolds numbers? Fascinating but intricate, boundary-dominated turbulent flows can yield counterintuitive phenomena like the Magnus effect. However, accurately simulating turbulence, especially when turbulent boundary layers are not fully resolved, still remains a significant challenge. To overcome this, we developed a novel approach that allows us to effectively mimic high-resolution simulation flow behavior using lower resolution, which is much more efficient, and we can reproduce phenomena such as the Magnus effect of golf balls, drag prices of spheres, and many other remarkable turbulent phenomena. Join our talk and unravel the secrets behind our method.
See you this afternoon. Thank you.
We contribute a new kinetic solver for incompressible single-phase fluid simulation with solid coupling. Kinetic solvers are used in both academia and industry because they run efficiently on massively parallel architectures, but their efficiency comes at the price of a very large memory requirement, namely an order of magnitude more variables per grid node than Navier-Stokes-based solvers. Existing LBM methods and graphics are memory hungry when simulations of high Reynolds number fluids are needed. In this paper, we introduce a lightweight and light-speed LBM solver that only stores 10 moments per grid node. Our method can solve incompressible fluid by streaming after distribution reconstruction and then processing moment-based collision. Now, we can simulate a hair comb moving around and creating fine vortices in its way. We also demonstrate two-way coupling examples, like leaves blown by a jet. Come and check out our talk.
Thank you.
Simulating water is captivating, yet in many cases, much of the computations merely result in plain transparency. Our innovative multi-phase solver breathes new life into those overlooked computations. Using traditional single-phase in-places solvers, our method can now simulate multiple fluid phases. Moreover, by ensuring the conservation of mass and momentum across all phases, our system can adaptively capture diffusion, stratification, and centrifugation effects. Because for us, every drop counts. Interested? Grab a cup of tea and dive deeper into our talk. Just remember, no cocktails permitted.
You know what happens when you add Mentos to Coke? I'm sure you will like it.
In order for you to live longer, you may need to do a simulation first.
Wow! Why does your simulator run stably despite such extreme volume changes?
If you want to know why, or want to see more cool effects, remember to listen to our lectures. See you.
See you this afternoon. Thank you.
Levels and methods have led the surface tracking in fluid simulation for their smoothness and accuracy, with volume loss being their main drawback. In this work, we propose GAM-NX preserve fluid volume. In our method, small droplets in splashes keep floating and dropping instead of smearing out. Our GAM-NX can not only preserve small surface structures, but also reduce numerical diffusion. Come to our talk to learn more.
Looks so delicious. Simulation? I need parameters. What? The rice grains get plugged in a realmeter? Oh no! Manually tweaking the parameters seems so hopeless.
Wanna try Volumetric? Record a video for a real-world experiment, then wait for the computer to optimize for the parameters, and record another video for another experiment, and wait for the computer to complete optimization.
Nice! I have the parameters! Looks so delicious!
Thank you.
We present Toros, a computational approach for automated design of soft robotic skins. Our method takes as input a pneumatic actuator dressed by a blank fabric and iteratively finds reinforcements that best approximate a given target shape under inflation. Using the same pneumatic actuator, we can encode different actions by changing the reinforcement patterns design, such as crawling or walking. Our method is driven by a three-field topology optimization scheme with a perimeter regularizer, which restricts the minimum width of the reinforcements and encourages compact patterns, improving the manufacturability of the design. Crawl to our talk to learn more.
Thank you.
As the popularity of the interactive and immersive VR and AR applications grows, so does the need for the real-time motion characterization. However, the characterized body proportion will not be exactly matched to the users, and the character may not even possess the human-like physics. So in this work, we propose a human-like introduce MoCA, a novel online motion characterization framework that transfers both the motion stylization and the motion retardation. Please come to our talk. Thank you.
Imagine you're designing a robotic character performing this animation. So you place motors at the joints of the rig. But motors are heavy, expensive, and take space. And you surely don't need all these degrees of freedom. So you try using fewer actuators, but with well-chosen axes. Well, easier said than done. This is the start of a long trial and error process. unless you use our method, which can find optimal design parameters and get you very close to the initial intent. More generally, our method takes any mechanism, even this complex spatial example with loops, and computes optimal design parameters given high-level targets. See you at our talk.
Want to capture yourself dancing? But 17 sensors is too much. Less, please. 11, 9, or 6? With only 6 sensors, every step, every move captured by our sparse poser. We've got legs in VR, in real time. Squat, jump, and sit. Sparse poser captures it all. Watch our talk to find out more.
Thank you.
Super resolution can implant great power to video games and enlarge the capacity of fancy virtual scenes. Previous works mostly focus on excavating details from history frames. We introduce Fuse SR, which involves low-cost, high-resolution auxiliary data to offer more reliable information. We design a new network architecture to align and fuse multi-resolution inputs into the same screen space. We further enhance our method using BRDF demodulation, which wipes out the high-frequency details from input images and restores them before final output. We have achieved significant improvement in both quality and speed. Read our paper to learn more.
Thank you. Image denoising has gained popularity as a technique for reducing noise in Monte Carlo rendering. While the existing denoising approaches effectively reduce some noise, they suffer from severe denoising bias. We propose a new mathematical framework for denoising guided by uncorrelated statistics. This framework enables unbiased denoising when an assumption is satisfied, and it can reduce some noise while significantly restricting bias, even when the assumption is not satisfied. For more detail, please come to our talk.
We present a novel adaptive recurrent frame prediction framework that can predict one or multiple extra frames in sequence, enabling huge flexibility to meet dynamic computational quotas in diverse visual tasks. We explore learnable motion vectors that combine the strengths of motion vectors and predicted flow, offering robust, subtle motion tracks for both opaque and translucent objects. Our framework supports the prediction of transparency, particles, and texture animations with improved motion vectors that capture shading, reflections, and occlusions, in addition to geometry movements. For further information, please refer to our paper. Thanks.
Microfacet theory suffers from energy loss in materials with high roughness. We propose a method to approximate the second bounce energy based on a simple geometric construction. Our approximation overestimates the energy from the second bounce and provides a more compelling approximation of the further bounces. Our method does not rely on any Monte Carlo simulation and is noise and artifact free. The cost of our method is close to GGX and is suitable for real-time rendering. Our results are visually pleasing and comparable to the gold standard in the field. Come to our talk to learn more.
Thank you. Spectrum mapping is a powerful representation that combines our method is able to render surface displacement as high quality on the GPU without tessellation. Thanks to improvement over previous work, we're able to pass trace and edit this scene in real time. Here, these scenes contain 20 billion macro triangles. So if you want to know more on how we render these beautiful scenes, please come to the detail session this afternoon. Thank you.
We introduce a locally adaptive level of detail technique for hardware-accelerated ray tracing. Our results are continuous in both space and time without popping artifacts. We guarantee watertight surfaces without T-junctions, or oh my God. We show that with custom hardware support and sufficient compute resources, we can achieve 10 times faster traversal while consuming less than 1/10 the energy.
Enjoying the beautiful scene in this photo, now you can look anywhere you want. With only a single image as input, our method constructs its expanded multiplane image, allowing free observation from a large range of perspectives. Our method achieves scene expanding and state-of-the-art rendering quality. To hear more about it, welcome to our talk. Thank you.
We present instant novel view synthesis. In this approach, we use point clouds as proxy geometry and supplement missing data with information from the closest images, similar to image-based rendering. In the used images, the environment of each pixel is encoded and then warped onto the point proxy before reconstruction. Our approach is designed to work on incompletely captured scenes and with no scene-specific training or pre-processing. This allows us to do instant novel view synthesis. If you're interested, please come to our talk this afternoon.
From the written words to captured voice, from static images to moving pictures, we've communicated our existence in myriad forms. As we enter the 2000s with video, we are left to ponder what new medium will define our future. Our answer is volumetric video. Immerse yourself in the world of volumetric video, where every angle is a new perspective and everything comes to life in full 3D. Experience reality as never before. Volumetric video is a game changer. By stitching together videos from multiple angles, it allows us to step inside a scene and view it from any perspective in real time. Please come to our talk to learn more.
We present INVS. Our task involves generating novel views only given a single image. In INVS, we use monocular depth to unproject source pixels and create partial views. Next, we use a 3D-aware inpainter to inpaint the missing regions and create novel views from them. Compared to our baselines, which garble details such as text, INVS keeps the text intact and legible. While our baselines struggle to preserve the underlying 3D structure, we find INVS to be more robust. For more details, please come to our poster or presentation today. Thank you.
I have a mesh. I have a sparse volume. Boom! Here's vMesh. vMesh is a hybrid volume mesh 3D scene representation that has great properties. vMesh is expressive. It's capable of modeling macro surfaces with mesh and thin structures with volume. vMesh is storage efficient. It takes less than 20 megabytes to store a detailed object reconstructed from multi-view images. And vMesh renders at real-time frame rates on consumer devices. For more information and online demos, please visit our project webpage. Thank you.
Join our session today. Thank you.